Okay, good morning everyone. Before we get started, I have to satiate my own curiosity. Can I see a show of hands of who considers themselves to be a programmer at all? Okay, cool, great, it's about half. I'm happy to hear that. So, my name is Nick Driscoll. My talk today is self-starting as a 3D graphics programmer. Let me begin by introducing myself a little bit. So, I'm a self-taught programmer since high school. I went to Ohio State for computer science. I currently work professionally as a DevOps engineer, but my true passion is programming real-time 3D graphics for games and studying it. I'm currently developing a physically based renderer in Rust using Vulkan, and I wrote this talk because I wanted to give new programmers who are interested in low-level graphics programming some sort of foundation for learning more about the field. So the agenda of this talk, it's relatively simple. The first thing we're going to do is define the technical problem of video game graphics, from a programming data perspective. Then I'm going to introduce the 3D graphics pipeline, which is the high-level algorithm of how you get 3D objects rendered onto a 2D screen. I will proceed into a detailed account of the 3 major pipeline stages, and then I'll end with a discussion of the various APIs that are available, debugging tools, research papers, presentations, communities, just how to learn more in general. So just a quick note, graphics is extremely complicated. No statements made here will be authoritative or 100% accurate in all cases that you can think of. And also, these slides will be available online after the talk. I have a QR code at the very end that can be scanned to get to those slides. So let's begin. Let's talk about video game graphics technically and what the task at hand really is. So video games display their graphics on a screen. And we're going to say that a screen is just a 2-dimensional grid of square pixels, like you have 1920 by 1080 at 1080p. Each pixel on the screen can be exactly one color at a time. And just as a vocab note, the current screen that you render to is called the render target, or also called the frame buffer sometimes. So to make graphics, the game has to draw/render these images by computing the individual color value of every single pixel on the screen for every frame. And yeah, individual images produced by the game are typically referred to as frames. That's just some terminology that you probably are all familiar with. But let's talk about the problem of getting 3D into 2D. So we have this grid of pixels that we want to fill out with colors, but then we have 3-dimensional information in our application, in our simulation. So first thing we're going to go over is how do we even represent a 3-dimensional object in a way that a computer can understand? And so the most common representation is that of a triangle mesh, where the surface of the 3D object you're working with is split up into a bunch of little triangles, and that just defines the surface. So in programming terms, you have one array of 3D vertex positions and whatever other data goes to the vertices, and another array of triangle connectivity information, i.e., which vertices in that buffer actually connect to each other to make triangles. And so together, those 2 buffers/arrays make up the triangle mesh data structure in your program. So what we are desiring here is some kind of algorithm that can take lists of triangles in 3-dimensional space as input and output colored on-screen pixels. So enter the 3D graphics pipeline. This is the main algorithm that allows programs to render 3D objects on the screen. Well, like I said earlier, it accepts a list of triangles as input, it outputs pixels as output. This pipeline is executed once for every object that you want to draw. And so we typically call one run-through of the graphics pipeline a draw call, which will be important later in the slides. And then I also just want to note that I'm giving the simplified model of you just put in triangles and it rasterizes your pixels, or it pops out colored pixels. But much of the pipeline's behavior is defined through configurable states that is defined in advance. We'll get to some code examples, and I will call out the variables that are supplied ahead of time by the CPU in advance. But let's just proceed. This is the 3D graphics pipeline in a very, very simplified view. So you input triangles, which are made up of vertices, and the first thing that happens to them is that they're processed by vertex processing, where all of the vertices in the triangles are transformed from their 3-dimensional world space position into the two-dimensional space of the screen. Then, once all of those vertices have been transformed into screen space, there's this step that runs called rasterization, where the coverage of the triangles on the screen is computed. In other words, you take all your triangles and you ask, okay, what pixels are actually being covered up by the triangle? So I will get on how this is actually a pretty easy step, but that's basically the main idea, is that it figures out what pixels are actually involved for a given triangle. And then the third step is pixel processing. So like now that you have all these pixels that were generated by rasterization, you have this pixel processing step that assigns all of those pixels to the color, and those color values are what gets written out to the screen. I have this illustration. So we have this like nice little 3D model of a cow. You can see how it's broken up into a bunch of little triangles, and you can see how like this triangle is kind of called out in this example. Vertex processing happens, the triangle appears in screen space, then rasterization happens, and you can see how like this triangle, which used to be a nice, pretty mathematical object, has now been, you know, uglified into a bunch of pixels, but of course this is necessary. Once these pixels have all been, you know, computed, then their color value is computed, and then you put that on the screen. So this is basically it. Like this is basically, you have your 3D data and you go all the way out to rendering it on the screen. And that's like it. Thank you for hearing me. No, I'm kidding. Like that's not literally it, but like at a high level, this pipeline is like all there is to getting 3D objects rendered on a screen, and everything in computer graphics, like all the beautiful techniques you've seen in modern games or whatever, they're all built on top of this foundation. So what I want to do now is I want to proceed with going through these pipeline stages in more detail. So the first stage, of course, we talked about was vertex processing. So like I said, for every vertex in a particular draw call, the vertex processing stage will run and transform them all onto the screen. But to be more specific, what happens is that this vertex processing stage is defined by a piece of code called the vertex shader. So the vertex shader is the code that defines what happens during vertex processing, and its primary responsibility is to, like I said, take vertices represented in 3D world space and output them into 2D screen space. The thing about it being custom code, though, is that the vertex shader can also do any other per vertex processing you might want to do. An example that comes to mind is like a tree blowing in the wind. You know, in your vertex shader, you might have the vertices sample a noise texture to like move them a little bit. So like, that is like one thing that would not just necessarily be transforming it into screen space. That is the job of vertex processing. Now, of course, I keep saying transform from 3D into 2D. This kind of naturally begs the question of like, well, how? Like, how do you take like a 3D vertex and put it into a 2D space? And while I didn't want this to become like a talk about mathematics, I am going to have to bring in some oversimplified concepts so that we can kind of continue without actually being too confused. So the two things you need to know about are vectors, which for our purposes, you can just think of a vector as like a point in space. That's it. And then a matrix is this mathematical object that represents the ability to transform a vector's coordinate system from one space to another space. And when I say the word space, I really just mean coordinate system. These are synonymous, basically. And yeah, so I'm pretty wordy bullet point here, but I really do want to say it because it's kind of like hard to comprehend, I guess. At least it was for me when I was new. Like, the whole point of this is that if you have a vector in a beginning space A, and then a matrix that transforms it from space A to B, like that matrix represents the ability to do that transformation, then multiplying them together will give you that exact same vector you had before, but now represented in space B. So yeah, I didn't want to go too far into the math on that, and like you guys can Google a linear algebra primer if you want to know like the ultra details of that part. But the bottom line is that all the vertex shader is doing is it's essentially just multiplying some matrices by a vector, which is the input coordinate position, and outputting it. Every object in the world will have at least one matrix that describes its position. And then there's also going to be a matrix, at least one, that represents the camera's position and various properties. You know, where is it positioned? How is it oriented or rotated? You know, what's the field of view of the camera? These are all things that are encoded into the camera's matrix. And so the following slide is going to be just a short little code sample, and I know that I didn't introduce how to program or anything. This is just GLSL, which is the shading language that OpenGL uses for writing vertex shaders and fragment shaders, or pixel shaders and whatever other shaders there are. You can see here, I'll just kind of walk through it. This is the input, a 3D position. And then this one line of code on 11 is the only line of code that's actually running. So we have this position, we multiply it by the object matrix that represents where the object is in the world, and then we multiply that by the camera matrix that represents how, given our camera parameters, we want to project that 3D into 2D, and then we just output that as GL position. And when I said earlier that there are inputs to the 3D graphics pipeline that aren't necessarily just the triangle lists, here is an example of what I was talking about. So right here, this uniform transform block with object matrix and camera matrix inside of it. This is the kind of thing that would have been set up in advance by the CPU before the draw call actually gets executed. So the idea is that these variables already have their data as soon as this code starts running, which is how this is able to work, right? And that's basically it for Vertex processing. I'm going to move on now to talk about the second step, which is rasterization. So after the transformation into screen space, the pixels that are covered by every triangle need to be determined in some way, and so that process is called rasterization. Now, lucky for us, as 3D graphics programmers, application programmers, the hardware just does this. You don't write a rasterization shader, you don't have to know how it works. You just have to output screen space triangles and you'll get pixels up the other end. I will mention though that even though it's not fully programmable, and even though you don't specify the behavior of the rasterizer in detail, there are certain things that you can configure. If you've ever seen wireframe rendering, that is just telling the rasterizer to draw lines instead of fill triangles, and multi-sample anti-aliasing is something that you just ask the rasterizer to do for you, for example. But there is something important about rasterization that I do need to get into your head somehow, and that is this idea of vertex attribute interpolation. Please don't be scared by this terminology. I will try to explain. So vertices in these triangles, in these triangle meshes, have associated with them some number of data points. So by default, they necessarily have a position associated with them, but they could also have, for example, a color associated with them, or any other data. When the triangle is rasterized, every pixel inside the triangle will get a value for each vertex attribute that is the interpolated value based on how far away from a given vertex each pixel is. And there's an example on one slide, but before I get to that, I just want to say that interpolation, if you haven't heard of that word, is basically just blending. Interpolation means to blend something. So here is my rasterization example. This is a very simple application that just renders one triangle on the screen. In the example here, each vertex has been assigned a solid color, solid red, solid green, and solid blue respectively. And then you can kind of see how every single pixel inside this triangle is getting a slightly different color value based on where it is in the triangle relative to the vertices. So a pixel right down there is going to be extremely blue, but near the middle is going to be very, very much a blend of the three colors. So this is just a very fundamental concept, because basically these interpolated values are the input to the next stage, pixel processing. So we now know all the pixels that are covered by our triangles, and we now want to assign them a color. And so then after we've assigned them a color, they can be written out to the render target, and we're done. So let's go over it. So you have, just like the vertex shader, this stage has a shader associated with it called the pixel shader. It is also sometimes called the fragment shader, depending on your API, but I'm not going to explain that right now. For each pixel that has been rasterized during the rasterization step, the pixel shader will execute and determine the color of the pixel. And so you might naturally realize this is where all logic related to textures, shadowing, lighting, anything else that's fancy. If any of you are tech artists or know VFX people and they talk about writing a shader, they're almost certainly always talking about writing a pixel shader. So now I'm going to move on to the most complicated example in the slide deck, just because there's 2 blocks of code. So this is kind of just putting that triangle example all together with all 3 stages. So in the Vertex stage, it's very similar to the example I showed you earlier. We get in a position like that last example, but we also get in a color per vertex, and then we actually output a color. So here in this code, you can see that we really do nothing more than just like directly output that color here. So that is like, for each vertex, you're outputting this F color, and the rasterizer is going to take that and interpolate it over the surface of the triangle. And so then the fragment shader is literally as simple as receiving that color and outputting it. Like, we're literally just giving frag color equals F color, and that should make sense to you if you understand like that the rasterizer is interpolating all these input values for each pixel in the pixel shader. And so you can imagine how like, you could have a normal vector or something that gets interpolated across to do like lighting calculations or whatever other data you want to be spread across the surface of a triangle. So that is like it for the theory behind 3D graphics, at least at a basic level. There are other things that I would consider essential that I didn't really have time for, but like if you are an interested audience member and want to go do this on your own, I will be showing you resources where you can like learn the handful of other things that like I thought were basic but couldn't really explain. So we finished covering the main theory, but how do we actually start writing code? There are a couple of things that I want to talk about. I want to talk about GPU APIs, i.e. how your program will actually talk to the GPU. I want to talk about debugging tools, which are invaluable always, but particularly invaluable for beginners. And then I want to talk about resources for getting started, as well as like the community, as best as I can describe it. Like, I'm not a guy who's like perfectly ingratiated to the graphics community, but I do have some inroads and I would like to share them with you today. But anyway, let's begin with graphics and GPU APIs. So just as a reminder for anyone who doesn't know or has forgotten, API stands for Application Programming Interface. It is the definition of how your application can interact with some kind of external system. And so in this case, that external system is the GPU, the graphics card on your computer. APIs for programming graphics can be sorted into two major categories though, and this has a lot to do with like the history of graphics. So I'm gonna call like older APIs, graphics APIs, which are like APIs that were designed more specifically with this pipeline abstraction in mind and less about like actually what the GPU is doing and like being able to program for it directly like the newer APIs. So I call those graphics APIs. Examples of that are Direct3D 11 and then older versions, OpenGL, WebGL, old console APIs, I assume. The second category I would call GPU APIs because they are much more interested in exposing exactly what the GPU is capable of doing, exactly what hardware is available to the application to use. So these APIs are always harder to use, but they are much more rewarding in the sense that like, as soon as you do grasp how to use these newer, lower level GPU APIs to like do graphics, you basically can like go do anything. Like there are certain modern techniques that are really, really hard to implement in the old APIs because they rely on like directly being able to program the GPU, but the new APIs don't have that problem. So examples of that are like DirectX 12, Vulkan, Metal, WebGPU, etc. That's really all I have to say about graphics APIs. Details about graphics APIs can be found on like the website of whoever maintains them, like Direct3D is like Microsoft, MSDN has the docs for that. OpenGL and Vulkan and Chronos Group APIs, you can look up Chronos Group to get their documentation. But yeah, moving on to graphics debugging tools. And this slide really should have said graphics debugging tool singular because there really is just one tool to rule them all here. It's called RenderDoc. It's an amazing, amazing, amazing program. If I have time at the end, I'll show it to you. It lets you take a capture of a 3D application, like one frame, and see all of the API calls that your application made to create that frame. And you can like see the intermediate results like as you go through it. It's very cool. I'll show it to you if I have time. It's invaluable for starting out. So there are so many moving parts to like getting something drawn on screen that like almost certainly if you go attempt to draw something on screen, you're going to just get like a black screen. Like, oh, what happened? It's a black screen. And there are so many places it could go wrong. But if you take a capture in RenderDoc, you can go through and inspect like every single thing in the pipeline and every single piece of data that you uploaded, and you can really easily pinpoint like where your application was wrong and like did something that was inappropriate or incorrect. If I'm going to talk about RenderDoc though, I also need to talk about vendor tools, and I also need a drink of water. So the GPU vendors are, NVIDIA, AMD, and Intel, basically. They each have their own tools that kind of do the same thing RenderDoc does, but better. Asterisk. Like, kind of the thing about these tools is that they are literally more fully featured, but they are really not beginner friendly. I will be perfectly blunt that I've only tried to use NVIDIA Insight out of these on the list, and like I don't really get it personally even. You can take a frame capture and like look at stuff, but it's just like way more. It's like information overload, whereas RenderDoc is really just amazing for beginners. And yeah, but I felt obligated to mention these because RenderDoc will fail you when you get to a more intermediate stage and you're doing some more advanced stuff. So that's vendor tools. Moving on to like resources for getting started. I wish I had more, but basically I really could only draw my own personal experience. So like one thing that really helped me was this website, learnopengl.com. Don't be fooled by the title. You don't need to use OpenGL to follow the lessons in learnopengl.com, although of course their code examples will use OpenGL. But it is a really easy to digest and relatively well-written tutorial resource for the basics of graphics. And they even have articles on like more intermediate topics like physically based rendering and stuff. But like their articles can straight up be inaccurate when you're going beyond like basic rendering topics. So I would just keep that in mind. But like if you choose to learn graphics, you will eventually just outgrow learnopengl.com, but it can be a great resource to start with. The other thing though that like I would consider totally essential, and I hate recommending something that costs money, but this textbook I got, Real-Time Rendering 4th edition released in 2018. Like it's kind of old. I think there's a 5th edition coming, but it basically covers like every single video game graphics technique that exists. It's really incredible. You can get a high-level understanding of basically like any of these techniques. You're not going to get a lot of depth just necessarily based on the nature of the book, but it gives you a ton of like vocabulary to look up, terms, the names of people, and of course it features a huge bibliography of like papers and stuff you can go look in. So you might be like, oh, I want to implement Bloom, and you're reading the chapter on Bloom, and then it's like, okay, I don't really get how to do it from this, but it's going to cite like a paper, and I can just go read the paper and implement it from that. Speaking of papers, when you are more intermediate, when you leave the phase of beginning graphics, you'll end up not being able to find tutorials for like the kinds of things that you want to learn. And that's kind of when you're at a position where you need to start getting comfortable with the idea of looking up industry presentations and papers. There's this convention called SIGGRAPH and this website called Artsiv that have lots and lots of papers for free you can look at. I also follow this newsletter, Graphics Programming Weekly by Jendra Gilner. Jendra Gilner is a graphics programmer at Ubisoft, like doing Far Cry. And it's a really great resource. It's like every week, all the hottest things that happen, and I really learned a lot from that. And then finally, I guess something that might be unexpected, but might be very expected for you, depending on who you are, is that one of the most invaluable resources of all time is Discord. So there is a very large and popular graphics programming Discord, which I have the link there, as well as a QR code in case you care to scan it. It is basically just a community of people who care about graphics programming, all skill levels, from beginners to intermediates to like true professionals who've been around for decades. They're really friendly. Their conversations are very illuminating. Like I was going to talk about posting, but like even if you just lurk and like read the conversations people have, like you can learn so much about like graphics ideas you never even heard of, but then also like how to debug. Like you might learn debugging strategies or like tools you never heard of or whatever. Like this community is just an invaluable resource. And one thing I'll also mention is that the APIs like DirectX, Vulkan, etc., they all have their own Discords as well. So like I'm in the Vulkan Discord asking questions all the time. And you can find all those Discords like from this main one. But yeah, absolutely invaluable, absolutely recommend if you care about graphics programming, getting this invite and going there. And then the next thing I'll talk about are, I'm just kind of thinking of things to mention to new programmers that, for graphics that might really be helpful. So some code libraries that I would consider totally essential. Everyone's heard of SDL. SDL is a library for doing your windowing and like event handling and other stuff too, but like that's mainly what I use it for. You know, it can be very tedious and cumbersome to like, oh, I'm on Windows, so I want to like look up the Windows API specifically and like, okay, how do I make a window? How do I do all this? How do I do all that? With SDL2, you just call create window and you got a window, and like then you can just focus on the graphics part and not the like operating system negotiation part. Really invaluable. GLM is a linear algebra library. It basically just allows you to understand less math. There are like a handful of common things that you need to do regarding the linear algebra that's applicable for 3D graphics, and GLM just has like a function call for creating a matrix or vector to represent whatever you need. It's pretty simple to like chain things together. It's very fast. You know, I guess it uses like SIMD under the hood and multi-threading, or maybe not multi-threading, but shouldn't talk out of turn here. Last library, Dear ImGUI is this amazing library that like if you have a 3D program, like if you have a program that uses a 3D API to draw stuff on screen, you can incorporate Dear ImGUI for your like developer user interface stuff. Like it just lets you have a really, really easy way of making like a window and with like radio buttons or checkboxes or text input fields or like scroll bars or you know value input fields or like whatever it is. Like you put Dear ImGUI in your program, it just outputs a list of triangles, which you know perfect, so we can like put them through our pipeline to get them on screen. And it's the greatest of all time. It's truly just, it's another thing that's like made by one guy. It's really, really like, it's really invaluable because like UI programming is in that perfect sweet spot of being like really, really simple and easy in theory. But then as soon as you go to do it, it's like the most tedious and error prone and obnoxious. And like you're spending all this time on it and all you're getting out of it is like, oh, I got some two-dimensional screen elements. Wow, that's very exciting. So yeah, Dear ImGUI I think is essential for like getting started or even just like prototyping. Like I know I watch GDC talks a lot and like in Engine for like Spider-Man they had Dear ImGUI like for doing debugging AI and stuff. So that's basically the talk, but I wanted to leave you with some words of wisdom just like from my 4 years of like trying to do this. First of all, start small. Your first program is almost certainly going to be just rendering one triangle on screen. That is hard. Rendering one triangle on screen is extremely hard, and when you do it, you will be accomplished, you will feel accomplished. All these 3D rendering programs start as just like a single triangle. You can't fear the feeling of being stupid because like, I don't know, maybe I'm just not smart enough, but I can't imagine a single person being smart enough to like go all the way through graphics and never feel like they were stupid. Like so much of the terminology is like names are similar. It's just hard to understand like what's going on. The theory is complicated. It requires like graduate level understanding of math and like physics, especially as you get into more intermediate graphics. And community is like absolutely everything. You really, really, really can't discount just how helpful it can be to go on Discord and be like, hey, I have a compute shader and it's messing up and here's how, and here's my error message. You will have people who are like, oh, did you try this, did you try that? And like, even if they're wrong, it will give you some kind of path to like go down and figure out the problem yourself. Yeah, that's really it for this talk. I wanted to leave enough time for Q&A because I know this is a really technical talk. I kind of assumed that there would be questions because of like how high level this all is. You can follow me on Mastodon. I have a website that sucks, and I have my slides. hey. And then I have like my slides in this QR code. Like all these slides are available. Here's an image from my render just to prove that I know what I'm talking about. This is all like from scratch, like just writing the code for it using libraries I said that I was using. But yeah, so I will now take questions. Yes?
So at the beginning there, you mentioned that you were building a physical or some sort of render.
Physically based?
Yeah, physically based render in Rust. What is your opinion of Rust as like a new programming language, and I guess what is the long-term vision for that particular, is that just a learning thing or?
So I just like Rust more than C++. I mean, Rust's design goals was to replace C++, at least that's my understanding, and like, while C++ is never really going away, Rust is kind of what I think of as like a younger C++ that hasn't had enough time to make all the mistakes that C++ has. I definitely can anticipate Rust becoming a language that's too bloated and that I move away from at some point. But yeah, I don't know. I don't have like a lot of language opinions. Rust is really just like the one that I know and it works well enough. Like it's a low-level systems language. It's very fast. It's relatively safe. It's nice.
And then with that renderer, is the idea to eventually like build that? Is that just like build that into something that would you use to put into a game engine, and then like what is the future for that project?
Yeah. Honestly, it's basically just a big portfolio piece for me to try to implement as many rendering concepts as I want. I'm available to be hired as a renderer, rendering engineer. But yeah, I mean, I basically got to this position because like I had 2 prior projects where I was like, oh yeah, I'm just gonna like make a game from scratch, no engine, no problem, all myself. And like I got to a point where like I actually had a pretty decent prototype of a VR game, I thought, but I just realized that I kept rat holing on like graphics concepts and like graphics problems to solve. And it was really just because like I think that's like really what I love the most is like developing technology. So could this be part of a game someday? If someone hits me up about it, but not like that's not like my plan right now.
Thank you.
Anyone else? Yes.
So I've never done any graphics programming. I just like make things in Unity. Let's say that I somehow go down this path and I make my triangle and I go further. What advantages are there to doing your own stuff instead of just like using like Unity or Unreal or some pre-made engine? Like what extra control do you get?
Okay, so I'm actually gonna kind of say that like if you're using an engine to make a game, you should probably just stick with that. The advantages of writing your own renderer are like coming to a deep understanding of exactly what your GPU is doing. Because I know for a fact that in both Unity and Unreal, there are facilities for accessing the low-level renderer, especially with Unreal Engine, which has like source code access, I guess. And so like, if you actually have an understanding of the 3D graphics pipeline, you can go read that code and actually get what it's doing. So, to be perfectly clear, I don't recommend like writing a game like this. Like this is just like how to learn how 3D graphics works. But like, if you're on a Unity or Unreal Engine project and the graphics suck and you're like, oh, what do I do? You actually will have some places to start instead of just being like, asset store. Anyone else? Sorry, you had your hand raised.
So when you import your models into your game, are you still using like this common standards like FBX or OBJs, or are you writing your own like programs to make the models as well?
So are you familiar with GLTF as a format?
Yeah.
So that's like, so Chronos Group makes OpenGL and Vulkan. GLTF is like supposed to be an open replacement for FBX, essentially. So my renderer understands how to load GLTF, and then it also has an optimized format. GLTF uses like a JSON string internally. It's extremely ugly and slow. So like I can load that, and so like if I had an FBX, I just like go to Blender and like convert it to GLTF and then like import it into my engine. And then in my engine, I have a button to like convert things into custom, faster formats. But yeah, right now it's just those 2 formats that my renderer supports. Yes, and you have a question?
What were some early learning pitfalls that you think would be really good to like advice that you give to like avoid that or just starting out with like the whole starting your own opinions?
That's a really good question. That is like really, really hard to answer because of just like how every single thing is so hard to do.
It's all a pitfall?
It's, I mean, like straight up, like graphics programming is just like getting out of a pitfall and then immediately stepping into the next one, like over and over until you finally make something.
Sounds like a cartoon.
Sounds like a cartoon, yes. I just, I don't know. I really can't even answer that. Like, really it's just like understanding your API, that's the hardest part. So like, if you're a new graphics programmer, I would recommend starting with like DirectX 11 or OpenGL as your starting API, and then like really making sure that like you read the documentation for the API so that like when you're in a tutorial or something and you're reading the terminology, you aren't getting confused. A lot of the terminology is like very synonymous, like it's very similar, and it's like 2 words that like are only slightly different, but they mean totally different things. So it's really easy to, if you don't give yourself a firm grasp up front about like terms, it's easy to get lost with the tutorials. yeah, I guess that's my answer. You?
Yeah, so you mentioned building triangle was kind of a big win. What would be a good second project to, what was like your experience when you made the first triangle? What was your next, like, wow, I really enjoy this moment?
Yeah, sure. So like, I guess the progression for me was like, after you have like a triangle like this, so you're like interpolating these attributes across the surface. So this is basically like, this is like one step away from being a textured triangle. Like getting a texture onto here is like what I would say next. And then as soon as you can get a texture onto a triangle, then I would think about loading a list of triangles from a file. You know, it doesn't have to be, you know, some like really common standard or whatever. It's just like the idea of if you can load models from a file and like have that triangle list, and then you can pass it through the pipeline you have created, then you basically have a program, you know. And if you use your GUI to make a little UI, you can even have like, you know, click a button to spawn the Windows dialog to click on the file, and then like your loading logic can load that file. So yeah, I guess right after you get the first triangle, I would say getting a texture on there is like what you would want to do. So you in the back?
View of the Blunderstreet. Do you have a favorite renderer?
A favorite renderer? I don't know. I like the Kojima engine renderer, like from Metal Gear Solid 5. I know it's kind of old, but I read the write-up on that a long time ago, and I always thought it was clever, so I guess that one. It's very pretty, yes. I thought I saw one more hand. Anyone else? Yeah, Kyle?
More of a comment than a question, but I can definitely say from the art side, having a better understanding of things like this has, I think, helped me produce like better models in animation, especially when it comes to like topology and knowing like specifically what's being rendered and why triangles. So important, like not just knowing how to import something into Animate, but like what's going on underneath to put it together, even though I still don't fully grasp it. I'd say it's been valuable for some.
That's a really great comment, Kyle, and I actually kind of want to just build on that, like, yeah, the output of the modeling team is the triangle list that is the input to here. So like, your artists and your 3D graphics programmers are like this. And yeah, if you understand like Vertex attributes or like, you know, Vertex packing or whatever is relevant in your case, you know, you can really make your assets a lot more optimal. Yeah.
And give you less of a headache too.
Yeah, and like, yeah, talk to your rendering engineers if you're working on a game. Yes?
So do you feel like there's tool sprawl in graphics program like there is in other programming?
Oh yeah, absolutely. There's definitely tool sprawl. That's kind of why I wanted to name drop RenderDoc, because like, if you take nothing else away from this talk, like if you're someone who is interested at all in writing your own renderer, and you take nothing else away from this, remember the name RenderDoc. That will save you countless hours of headache. But yeah, I guess to answer the question, like yeah, there are a million tools for everything. Every vendor has their own version of their own way of doing X, Y, or Z. If you really, really want to get a full picture, you really have to end up going on like NVIDIA's website, AMD, Intel, going on the Discord and asking people. Like honestly, going on the Discord and asking people stuff, especially as it relates to like the wider culture of 3D graphics, is really just the fastest way to like learn stuff. So yeah, but yeah, there's a lot of tools for all. That's the answer to the question. Well, if that's really it, I'm willing to call it and let you guys go early. Any more questions?
I have a question of the camera matrix.
Yeah.
So if I wanted to compare that to like more like a physical camera, does the camera matrix like take into account like different lenses I'm using to project the image that I want?
Yes. When you are learning 3D graphics at the start, you have this approximation of a camera called the pinhole camera, which is like not really physical. But yes, if you get more sophisticated, the camera matrix is broken up into two matrices actually, called the view matrix and the projection matrix. The view matrix is like where it is in the world and how it's oriented. The projection matrix is all the camera properties, including focal length, field of view, aspect ratio, all that stuff.
That makes sense.
Yep.
After your first triangle, do you have any suggestions for like how to build on that? And
I have like, I definitely am a guy, so like I've been studying this for 4 years, but I wouldn't even say that I have like 4 solid years of experience in the sense that I'm very on and off about this. Like I've been working on this renderer pretty consistently, like this one, pretty consistently since February of 2022. But like, you know, I'll have months of inactivity sometimes because I'm tired or just don't want to, or how do I find a balance? I get excited one day and then I start doing it again. Yeah, anything else? You got 5 minutes. Yes.
So in this example that you have on the screen, you've got lights and shadow. Is that texture? Is that a more advanced concept, or?
So what I will say is that these shadows are implemented using textures, but like when I was saying like getting a texture on a triangle or whatever, I was literally just talking about like getting, man, this is hard to describe. Just like getting an image mapped onto a triangle surface in the first place. These shadows do use textures, but it's more advanced than just simply putting the texture on the triangle like you would in the most simple case. Sorry, I'm having a hard time like dumbing it down, I guess.
Is
But
that
like,
more intermediate maybe concept or advanced concept than?
yeah, and like these lights aren't real lights in the sense that they don't cast lights onto other objects. These are just really, really bright surfaces that are being bloomed by the bloom effect that I implemented. So, and that's like a post-processing effect. I guess I can speak for like 1 second about post-processing effects. So like, after you're done doing all your 3D graphics pipeline work and you have all your 3D stuff rendered on screen, it's very common to have an additional step where you take that 2-dimensional image that you've rendered and you just start doing 2-dimensional image effects on it. So like, you know, I said I was gonna go to RenderDoc if I had time, and guess what? So I have time. Let's take a look. So here's RenderDoc. Here's like an example of like going through various draw calls. So like you can see how like, you know, as I go through here, more and more pieces of Samus are getting drawn. And, you know, let me, it's being real slow. Holy moly. Excuse me. What in the heck? Okay, so I was going to just get this up. Yeah, that's totally visible.
Yes.
That's like pre-bloom, which is the funny part. So, yeah, let me put this like this. Yeah, hold on. What the heck is going on here? So yeah, okay, yeah. I was trying to like be able to flip back and forth between like the non-bloomed image and the bloomed image. So let me see if I can do that by like clicking on this. Okay. Yeah, okay. So you can see how like, you know, Samus's visor and like, you know, the yellow parts here and stuff, those are really, really bright surfaces. But obviously like in the 3D graphics pipeline, when you're rasterizing these triangles, you know, you're only able to affect the color of the pixels that the triangles cover. So for effects like bloom, where it's like, oh, the bright surface is like kind of bleeding over the edges of the pixels, you have to do post-processing effects. So like, you would take a 3D render like this and do some code on it and get a result like this. Yeah, that's just post-effects. I just figured I'd say that since I had some time. What's up, Kyle?
So would that be, if I had to make like an example, could that be like the equivalent of if I was like making a miniature and then painting it, and then took a picture of it, and then use effects and filters to make lights and things shine and shadows and or something like that?
To use that analogy, taking a picture, like the raw process of your camera's like film receiving photons and making an image, that's like the 3D graphics pipeline. And then any color changes from like codecs or Photoshop or whatever, that's all post-processing effects. So yeah, perfect analogy. And that's about it. We are actually out of time now. So thank you all so much for listening to my talk. I really hope you all got something out of it. Yeah, thanks.